we have what we call the truth table. That for the computer to evaluate whether that statement, whether that complex statement that has been formed by the either or logical connective, it uses what we call truth tables. Every logical connective has a unique truth table. So what is a truth table? A truth table is a method of mapping out all possible truth values in an expression together with their resultant outputs for a logical operation. What are we saying? Is that if you have two simple propositions which have truth or false values of T and F, and then there is a logical connective that has been applied on those two to form a complex proposition of P plus Q, then for you to get the value, the output, you use a truth table to first of all represent the input side and then to represent the output side. So you represent all the possible truth values of or all possible ways those statements can be combined, yeah, and then you also find out the possible resultant values of how those compound propositions will turn out. Therefore, in that truth table, I have shared an inclusive OR truth table, yeah, that for an OR operation P and Q read as a disjunction P and Q, or either P and Q, values can be summarized in an OR inclusive truth table as follows. Okay, so what do we do? That if you want to get how many rows that truth table would have, because it is a binary representation, you always say the formula is 2 to power n to get the number of possible combinations or rows that you are going to have for that truth table. So for this case, we know that we have variable P and Q. So to find out the number of rows we are going to have in the OR truth table, which is working on P and R and Q, we shall say 2 to power 2, which is equal to 4. So our truth table for inclusive OR will have 4 rows that represents the true and false values. So on the left side where we have the input, we shall be able to put our variable P and Q. Then we shall start representing the possible combinations of the input values of false and true. So we usually start with the first combination, that what happens when Q is false, when P is false and Q is false. Then the next point would be, what is the result value when P is false and Q is true? What happens when P is true and Q is false? What happens when P is true and Q is also true? Yeah. For those who know binary, you can represent briefly. You can see that when you combine that in terms of binary, you will find that it is 0. The first one represents 0, 0, 0, 1, 1, 0, and 1, 1, which actually represents 0, 1, 2, up to 3. Okay? Now, on the output, how do we determine the output when an either or operation is carried out on the truth values? What happens is that we have a standard evaluation or interpretation mechanism for an either or, that whenever there is any either or operation that is carried out on certain inputs of truth values, the result will always be true. Okay? Whenever there is any truth value in the input. Otherwise, it is false. What do we mean? Is that so long as there is any propositional variable in the input which is true, it doesn't matter how many other false exist on other variables. The resultant output will always be true. But you can only get a false output in an either or operation when both value or all values you have in the input are false. Okay? Now remember, you can represent the truth table using the T and F's, but also you can represent them using the zeros and ones as on the right hand side. Now, I think that interpretation is clear. So we can do the same if we go to, we have now been able to see what happens on the inclusive OR truth table, and we have seen how we can be able to read the statement. Now we go to an AND logical connective. I've already told you that the AND logical connective, or what we call the conjunction, is always used to carry out a multiplication operation, okay? And we shall use the same, we are still using the same proposition. P is equal to Henry eats apples, and we have Q is equal to Catherine eats chocolates. If we combine the symbol proposition using AND, we shall say Henry eats apples and Catherine eats chocolates. Henry eats apples and Catherine eats chocolates. We can represent that as mathematically using the variable P and Q, and we can say P conjunction Q, or P times Q, or P asterisk Q. You can represent that mathematically, okay? Now, to evaluate the truth value, we shall still say that that truth table will need to have 2 to power 2, which is equal to 4 columns, rows, for truth values. And then on the other side, subsequently, we shall find out the output. Now, similar, a little bit different from the either or. While the either or, we said that for any true value in the input, it will always result into a true value in the output, irrespective of how many false values are there. You can only get a false value for the either or if all the input are false. Now, this is a bit different from the AND. That for the AND, what the computer would evaluate would be that it can only give a true resultant value if both or all the inputs are true. Okay? Otherwise, it will always give a false result. What do we mean? That if you have false and false, you will always get a false result. If you have false and true, you will always get a false result. If you have true and false, you will always get a false result. But where you have true and true, you will get a true result. Okay? Now, the not. Not is a negation. What it means is that with the not logical connective, it always gives the negative of what is available. And we have been able to demonstrate there that if P means Henry eats apples, negation P stands for Henry does not eat apples. So it just represents the opposite. And we can represent it negation P. Okay? Now, in the not truth table, every false value will get a true result, and every true value will get a false result. So it's always the opposite of the other. Now we come to this NOR, the NOR connective. We have told you the NOR connective is the one that uses neither nor. So where we have our values P and Q, still the very same proposition, Henry eats apples and Catherine eats chocolates, we can represent them mathematically by having P plus Q. But because it's the opposite of NOR, you just negate the whole addition, okay, as indicated in that equation, okay? Now, the NOR truth table. The NOR truth table, you will have still the same number of inputs, okay? But what happens in the NOR truth table? That it's going to be the opposite of the OR table, okay? Because it's not OR. So whatever was true in the OR table becomes false. Because we remember that in the OR table, we said that for any true input, you will always have a true result. But you can only get a false output if both or all the inputs were false. But this is going to happen in the reverse in terms of the NOR table, okay? And what the statement here, you can read it is, if, for example, you combined the proposition Henry eats apples, and then Q is the proposition Catherine eats apples, I can use it to say neither Henry eats apples nor Catherine eats chocolates. Okay? Then we shall look at the NAND. NAND means not both. It is the opposite of AND. So if we have the proposition, Henry eats apples and Catherine eats chocolate, then we can read to say Henry doesn't eat apples and Catherine doesn't eat chocolate. And it can be represented mathematically as PQ negated. Okay? So the NAND truth table, again, like I've told you, it is the opposite of the AND. Whatever was true in the result of AND will become false, and whatever was false will become true. Then the XOR, what we call the exclusive OR table. The exclusive OR. Now, in the exclusive OR table, you are simply saying that we usually use the term either dash dash or, but not both. So this is a little bit different from the NOR. It is a little bit different from the OR, in the sense that while the OR, you always say that any truth value should result into a true output. When you are talking about the XOR, the exclusive, it simply means, when you are talking about exclusive, it means either the other one has and I don't have, or I have and the other one doesn't have. But if we both have, it is false. So for an exclusive OR truth table, the difference with an OR table would be that the true value, when the true values, both values of Q and P are true, then they will still be false. Because we are talking about exclusivity, we don't want a situation where both of them are true, okay? And the truth table will appear as it is. Then we have, finally, we have what we call the XNOR table. Now the XNOR table would be the opposite of the XOR table. Okay? So what happens that you have P, Henry eats apples, and Q, Catherine eats chocolates. So you can read that statement that the compound proposition will be read as neither Henry eats apples nor Catherine eats chocolates, but both. That's how the statement. So you have the neither nor, but at the end you add but both. So with its uniqueness of being the opposite of the XNOR, it means that whatever was true in XOR becomes false. Okay? Becomes false. So for example, this one, it's also you can also call it the truth table of equivalence. That if the truth values was 0, 0, if P was 0 and Q is 0, then the final result will be true. And if Q is 1 and if Q is 0 and P is 1, the result will be 1. Okay? If P is 1 and Q is 0, the result will be 1. But if P is 1 and Q is 1, the result is 1. Oh, sorry. If we are saying in this case is that where the two input values are the same, 0, 0, the result is 1. But where it is exclusive, the result is 0. But again, where the P and Q are also 1, the final result is also 1. Okay? Therefore, I hope that you have enjoyed this lesson. We shall be able to add the if-then and the equivalence statements in the next class. But I hope that you can be able to make practice. You can now, I hope that after this class, you've been able to appreciate how computer manages some of these logical expressions. You have been able to understand how the computer logic varies from our human logic. Or you could still be able to understand why the computer carries multi-million instructions in microseconds. As human beings engage in complex thinking and reasoning about situations, applying emotions, the computer turns all those statements only into zeros and ones. And that is the reason why it's able to perform multi-million operations in very few seconds, because it does not have to evaluate the complexities of those statements. We shall be able to look at arguments in our next class to be able to see how the if then and then the if and only if statements are used to carry out those operations. And we shall give simple assignments for you to do. Just make sure that you subscribe to this platform to be able to get more of those additions. We shall be able to get other colleagues who will be able to take us through other topics. We are collaboratively teaching this module, and I hope you can enjoy it and it's useful. Make comments how you are finding this video, and thank you and God bless. Bye-bye.